Ma'am, shall we start?
Yeah, you can start. 3 minutes we gave me.
Yes,
I
now
think
28. Many students are
Aditya
also
also not
joining in
joined,
between.
I think. Hmm.
Yeah. So, Senthil sir, shall we
We
move to the
started.
session?
Yes, sir.
Okay. So, welcome all. The second day of the workshop of Design Expert Software. Our resource person, Dr.Senthilkumar sir, already joined with us. So, we will proceed to the session. Welcome you, sir. Hand over to you, sir, to the session.
Okay, thank you, sir. Thank you, madam. Okay, in continuation with the yesterday's session, we will be moving on to two important techniques today. And the first one is Taguchi's design of experiments, and the second one is response surface methodology. So these two techniques are very, very important in optimization, and you can see n number of papers in elsewhere or Springer journal involving chemical engineering process optimization using these two techniques. So today I am going to solve problems in both the Taguchi's optimization and also in response surface methodology. So first we will start with the Taguchi's technique, so which is a simple tool. Okay. So first I will tell you some of the basics that is related to that, and then we will move on to the hands-on training. So is the slide visible, sir?
Yes, sir. It's visible now.
Okay. So I will take 5 to 10 minutes in explaining the different concept that is behind this Taguchi's technique. So Taguchi, as a design of experiments, has got the name from the famous statistician that is Junichi Taguchi. So who is a Japanese scientist, and his core area of research is improving the quality of manufactured products. So quality should be inbuilt. So that is the mantra behind Taguchi's approach. So quality is not an external one; it should be inbuilt. So this Taguchi's technique have least number of experiments than that of the full factorial designs or response surface methodology and all. So most of the Western statisticians don't accept this technique. But nowadays, in most of the industries, this Taguchi's technique is being accepted and lots of work are being done in this. So where he started his research in designing experiments. After World War II, the telephone system of Japan was highly damaged. So he was given the in charge in order to develop the communication system in telephone. That's where he has coined the term signal to noise ratio. So yesterday itself we have seen signal to noise ratio. So the signal quality will be good when the external disturbances, that is noise levels, are low. So that he has coined only in this telephonic company. So the major contribution that Taguchi has provided is quality loss function, orthogonal arrays, that what we will be speaking today. So orthogonal arrays and linear graph. So that is our area of interest today. And then robustness. So robustness is it can withstand whatever the external disturbances are. So this system that Taguchi has provided is robust in nature. Okay. So this and all I will omit. Right. So what is novel in Taguchi's DOE? So he is designing the experiments. So as told, quality should be inbuilt, right? So his approach is not only to improve the quality, but also to quantify how much improvement is being made, right? So he is going to do some works in order to improve the quality, but how much improvement, that quantification is also made in the experimental design itself. One more important aspect of going with this Taguchi is these techniques are very, very easier, okay, to understand and also to work it out. Okay, so these Taguchi's DOE, we normally call it as DOE, design of experiments, is very easier and user friendly, and it is consisting of standardized orthogonal arrays. So that standardized orthogonal arrays, we can download it from any website so that we can design our experiments accordingly. So there are many softwares. Okay, Qualitech is one of the software. Then we have DOE++, another software. JMP, that is another software. Minitab is another software, and the Design Expert is another software. But while going with this Taguchi, Minitab is a very good software, and it is all user-friendly software. So most of the researchers will be using Minitab. So that you should be very, very careful. It's Minitab, MINITAB, not MATLAB. MATLAB is different and Minitab is different. Okay. So he has designed the experiments by developing some special orthogonal arrays. So these orthogonal arrays are based on Latin square designs. Okay. So the novelty of Taguchi's DOE is analyzing the outputs by means of signal to noise ratio. He has used some simple formulas to calculate the signal to noise ratios. Okay, because the signal quality should be good. Okay, when it will be good? When the external disturbances, that is noise levels, are lower. So by this we are going to determine the optimum conditions. Okay. This is all we have seen earlier. This is what we are speaking about. So yesterday we have seen 2 power k design, that is full factorial with the 2 levels. Okay, so here we will be having, so up to this, up to 15. Okay, so up to 15 you can see. So this is 2 power k. So the number of factors is 3 and the number of levels is 2. So 2 power 3, which is equal to 8. So that we have obtained. In the second case, it is 2 power 7. So that is 128. And in the third case, 2 power 15. So that is 32,000 something. But in this case, you can see, where is this 32,000? Where is this 16? So this drastic reduction of experiments is possible with the Taguchi's technique. So that's why most of the Western statistician does not accept this Taguchi's technique, because 32,768 experiments you have to do with 15 factors, that is varied through 22 levels, 2 power 15. But here in this case, you can see it is just to only 16 experiments. So a drastic reduction in experiment is there. But what effect this 32,768 experiments will provide us can be obtained by these 16 experiments. Okay, you have to understand that the effect of input parameters determined from this 32,768 experiments will be same as that of the effect that is produced by 16 experiments. Okay, so that's what this Taguchi is trying to tell us. So in coming in the 4 and 5, in this later stages, it is 3 level factors, 3 power k. We call it as the 3 power k because each and everything we are varying by 3 levels. So here 3, you see it is just 9 experiments. So 3 power 13, the last you can see, it is 15,94,000, but it is only simple 27. Right? So this is what the Taguchi has provided to us. In this 27 experiments, the quality is inbuilt, and also the quantification of how much improvement can also be quantified. So that is the advantage of going with the Taguchi's design. Okay. So this lattice square and all we can see later on, right? So this is what we are going to be. So in lattice square experiment, we will be using this L. So L9 orthogonal array, L16 orthogonal array, L18. So that L stands for orthogonal array. L9, that is A. A is nothing but how many experiments we are going to carry out. If it is L9, then 9 set of experiments has to be carried out. Then B power C. So C is the number of columns, that is parameters. And B is the number of levels. If I'm going with the 2 levels, then 2 power. If I'm going with 3 levels, then 3 power. Okay, so here take it as an example. L4 2 power 3. So this 4 is nothing but 4 set of experiments, 4 rows, and 2 levels, 3 parameters. This is 3 parameters varied through 2 levels. We can have L4 orthogonal array. So in the 3 series, you can take this L27. So 27 experiments we are going to carry out for 13 inputs, that is varied through 3 levels. No, sir, I want only 6 I have only 6 variables. Which one I have to choose? So you can choose L27. The remaining columns we have to delete. So these are the simple cases. And apart from this regular level series, that is, if all the variables are varied through 3 levels, you can choose this. If all the variables are varied through 4 levels, you can choose this. But what happens when the levels tends to vary? That is, one parameter we can change only 2 levels, whereas in the other parameters I want to change it to 3 levels. Then it is called as a mixed level design. Because one parameter I am going to vary it by 2 levels. The second parameter I am going by 3 levels. So here you can see L18. So 18 set of experiments in which one parameter can be varied through 2 levels, okay, and 7 parameters can be varied through 3 levels. So this mixed level series is not possible with factorial.
Excuse me, sir.
Yes.
Sir, what is this?
Yes.
4 rows means what, sir? The 2 raised to 3 means we are 2 into 2 into 2, no? 8 is coming.
L4 is number of levels 4. Sorry, number of experiments that we have to carry out is 4. 4 different sets of experiments. 2 power 3 it is coming as 8, no, madam? 2 power 3 is 8. That is the maximum one.
Okay. So
okay,
4
that is 3 parameters.
Set of experiments we have to conduct, no?
Yes, ma'am. 4 combinations of experiment we have to conduct. For 3 parameters that is varied through 2 levels.
Okay.
So normally in full factorial we will be going with the 2 power k. So 2 power 3 is equal to 8. 2 power 3 is equal to 8.
8. Okay.
But in this, it is just half of the experiments that we can do.
Okay. Full factorial level, we have to conduct 8 experiments, but in this case, we have to conduct 4 set of experiments. Right, sir?
Yes, ma'am. Yes.
Okay.
So I will explain with this L9. L9 also I will explain. You can see here L9, 3 power 4. So 3 into 3, 9. 9 into 3, 81. 81 into 3, 243. But here you can see only 9
experiments. 3 raised to 4 is 81, sir. 3 raised to 4 is 81 also.
So 3 into 3, 9, ma'am. Oh, yes, 81. Sorry, 81.
81.
For 81 experiments, we have to go with just 9 experiments.
9 experiments under Taguchi method.
Taguchi method, the effect that what will be obtained from the 81 experiments will be obtained in this L9 experiments itself. So that's the beauty of this Taguchi's technique.
Okay, sir.
Okay. So first 8 steps in Taguchi is state the problem, determine the objective, whether we are going to maximize or minimize the output. So that we have to determine. Then determine the response. Then I have to measure it. Then I have to identify the influencing parameters. Then I have to identify which is the influencing parameter and which is the noise parameter, that is external disturbances. Then I have to segregate. Okay. Then in this noise levels and all, something I can control and something I cannot control. For example, in your experiment, okay, the temperature, the atmospheric temperature or the pH, we can control at something, but something we cannot control and it is beyond our limit. And dust factors we cannot do. So that are all noise factors. Okay, then identity factors that can interact with each other. For example, 3 parameters I am going to select, A, B, and C, in which if I am going to combine A and B, what is the interaction effect on the output? So that also we should identify. So this can be done only we have an expertise in that area. Only when we have an expertise in that area. Then based on that, how many parameters we are going to select and how many level values we are going to select, we have to select the orthogonal array. So I will tell you how to select the levels, whether it is 2 level, 3 level, or 4 level. While doing the hands-on training, I will tell you. Then assigning the factors. So don't worry, get worried about this. The software itself will take care of everything. But just we have to enter and we should know how to analyze that. Okay. Then conduct the experiment, record the output values. Then I'm going to analyze. I'm going to interrupt the data. Then I'm going to determine the optimum conditions. And then I'm going to predict the output. For the optimum condition, what will be the output? That also I can predict. Okay. So this is the steps in Taguchi's DOE. And the most important thing of all is running a confirmation experiment. Once I obtain these optimum levels of inputs, we are going to predict, no? So whether this is good, whether it is correct or not, how we are going to get that. So for this, we are going to perform the confirmation experiment and the output should match with this predicted value. Then only the optimal levels what we have obtained will be really good. That's why at the end, we have to do the confirmation experiment. Okay, so this one all I will skip it out. Right, the orthogonal array selector. So this is kind of tables we can download from internet, Google it, orthogonal array selector. We can see, right? So 4 parameters, 3 parameters. I go with 3 parameters. That is varied through 3 levels. I can go with L9. So this is my L9. 3 parameters varied through 4 levels. I have to go with L16. So based on this also, I can select which orthogonal array that suits my selection of inputs and its level value. Okay. So this is what we are speaking about. L4, as madam has pointed out, L4. So 4 experimental combinations we have to carry out. Okay. So this is 2 power 3. Normally it will be 8 in full factorial. But here you can see it is only 4. It is only 4. Similarly, L8. 7 parameters varied through 2 levels. So we are speaking about levels, 2 levels. This is the first level and this is the second. That is 2 values for these parameters. It may be 100 pH value, for example. 2 levels means
Sir, sir, can I ask one more? Sorry for the interruption.
No issues,
how
madam.
we are getting it is already different. How we are getting these 4 experiments we have to get from Taguchi that I didn't get you, sir.
Madam, this is based on the Latin square. So this is based on this. Taguchi has used yes, this tables, madam. Actually, it is an n into n table.
Okay, sir.
So based on this Latin square only, he has developed that array.
Okay, okay. Okay.
Okay. So it has some basics. If
Hmm.
you go in depth, then it will be a different presentation.
Okay, sir. Okay. Okay.
Okay.
Okay, sir.
So now what we are going to do is we are going to couple these two Latin squares. We are going to couple and then we are going to obtain this. So this
Okay.
is what we are going to call it as the orthogonal array. So from the Latin square, we are going to obtain this orthogonal array by combining two or superimposing. We are going to superimpose one Latin square over the another Latin square, and then we are going to have this orthogonal array. Okay, so don't worry about that. The software itself will take care of everything. Okay,
Okay. Okay. Huh.
so in Taguchi's approach, these three formulas is very, very important. So this is my objective. Smaller is the better. For example, what to say? The residuals in your study, it has to be as low as possible. But the removal efficiency, it has to be higher. So the residuals, it has to be lower. So for this, we should have this formula. So S by N, signal to noise ratio is nothing but negative 10 log of. 1 by N is nothing but the number of replications. N is number of replications and Y is the output. Okay, individual outputs that I have to sum. Okay, so similarly, the larger is the better. For this, this is the formula. You can see this is yi square, this is 1 by yi square. That's the difference. And nominal is the best. So this we call it as the target values. For example, if I am going to do some machining process, then the surface roughness should be this only. I am going to fix it as a target. For example, the pH value, it should be 7, neutral. That you can fix it up, and that is the nominal, the better, best. So likewise, these three formulas we will be using in Taguchi's technique. Okay. So this is the formula that we are going to use for prediction purposes. Okay. So here I am going to have three parameters, A, B, and C, three parameters. Okay. So by using these formulas, we are going to predict the output for optimal condition. So finally, I will be getting an optimal condition. So for that optimum condition, what will be the output that I can predict by using this? So what is this optimum? So the optimum condition that relates with the A parameter. So likewise for B, likewise for C. And this is the overall mean. You can see this. Overall mean of that. So by using this formula, we can predict. Right? And also, finally, we have to do one confirmation experiment, and then we have to correlate this predicted thing with the confirmed results, and actually, it will be very close to each other. So that's how that is the supremacy, or what we call it the supremacy of this Taguchi's technique. So with this basic introduction, we'll move on to this software. So this is the Design Expert 12 front end. So file, new design. So in which we are going to have standard design, factorial, randomized, and then miscellaneous. You can see. Okay, standardized. In standardized, it's factorial. In factorial, it may be the randomized. Then miscellaneous. In miscellaneous, Taguchi OE. OA is nothing but orthogonal array. So here you can have the different designs. So how many parameters? You can click this. Then you can decide which orthogonal array to choose. So depending upon our number of input conditions and in which each and every parameter can be varied by different values. So how to select the level values? Right. So in my condition, the pH cannot be varied that much. We can vary it from neutral, for that is 7, Either 6 or 8 I can vary, or at the most I can vary to 5, 7 or 9. So that is very, very close. When the values are close, we have to make it short. So less number of level values when the range is small. For example, 100 to 200, it is very small. So I can take 100 and 200 itself. But when the range is higher, for example, 100 to 2000 or 100 to 1000, then I have to increase the number of levels. For example, 100, 300, 700, 1000. For example, I am telling that. So if the range is higher, then higher number of levels will fetch you good results. If the range is smaller, then we can restrict our values. That is the level values. So this is the ordinary thumb rule that we will be following in selecting the level values. So in this case, I will be going with the L9 for example. I am going to choose some example in which I am going to have L9 orthogonal array. So in this example, I am going to have one example that is related to that. So I am taken that from an base paper. The title of the base paper is Taguchi Optimization Approach for Phenolic Wastewater Treatment by Vacuum Membrane Distillation. So which is related with the chemical engineering. Okay, I am going for a phenolic wastewater treatment in which they have considered 3 inputs. The first input is pore size. Okay, then the percentage of porosity, then thickness. Okay, so in this, for standard L9, it will be 4 parameters, but I am going to choose only 3. Then what happens to the 4th case? Just delete that column. That's all. So the first one is pore size that I am going to enter. And second one is percentage of porosity. And third one is thickness. As I am not interested in the 4th category, I am just going to leave that. So now what is the levels? I cannot change this because L9, it is only for 3 levels. So I cannot change these levels, only 3. In the pore size, the values that I am going to have. Sorry, they are using feed temperature. Sorry, it is not, sir. So feed temperature they are having. And the second one is vacuum pressure. And third one is feed concentration. So that is varied by 3 levels. In the feed temperature, they have taken 45, 55, 65. So 3 temperatures they have taken. And in vacuum pressure, they have taken 30, 60, 90. That I can enter. And in feed concentration, I am going with 20, 510, and then 1000. The unit is milligram per liter. The vacuum pressure it is millibar. In the case of temperature, it is centigrade. So that also I can enter. Okay. So now I have given the name of the inputs, its unit, the level values. Okay. Then I am going to click next. So this is the intercept and all. So don't worry about this. Based on this only, the design will be developed. Then how many response we are going to have? So in this case, they have taken only one factor that is called as separation factor. They have taken the separation factor. Okay. So here I am initially I am not going to select this. Power not defined when the residual degrees of freedom is 0. Okay, finish. That's all. So as I don't want this B, because I am not going to assign any input to this D column, I am going to just right click that and I am going to just delete. That's all. So L9 I have altered according to my requirement. So it is normally suited for 4 factors. But since I am going to have only 3 factors, I can delete the 4th factor. Okay. So for this, I have to enter the value. For this, I have to enter the value. So previous itself, I have this value. So according so this is the values that I am going to paste. So now I have performed the experiment. So as madam has rightly asked, so the first experiment should be conducted with this combination. The feed temperature should be 45 degrees centigrade. The vacuum pressure should be 60 megabar or millibar, and the feed concentration should be 5 ton. Okay. Then the second experiment should combine this, and I have to determine the separation factor. So in the previous session itself, I had told in design of experiments, we are going with 3 important concepts. The first one is randomization, then replications, and third one is blocking. So here you can see first 2 columns, standard and run. So first I will right click, sort ascendingly. So this is the design. But why we are going with this run order? That is, it is being randomized. The purpose of randomizing is to reduce the experimental errors. The purpose of randomization is to reduce the experimental errors. So I have to go only with this randomization or run order because it is the randomized one. Okay. Sort ascendingly, and then I will go with this. Now I will go with sort ascending. So now I am going to analyze this output. Okay. So on the left side you can see the analysis, separation factor. So initially I don't know what to do, so I am going with the no transformation. If the residuals is higher, then obviously I have to go with the transform. Otherwise, there is no need to transform the raw data. Then effects. Okay, you can see it here. You can also see it mean. But in this study, what I am going to do is, I am going to consider only the main effects plot. I am going to consider the main effects plot. Initially, it was like this. You can see here the inputs are in error. So what I am going to do is I am going to right click this. I can change this into model, or in the process order I can change it to main effects. That's all. Okay. So this is the value of that. You can see the probability values. Okay. So now I will be going with ANOVA. You can see. So this is an example. Okay. So the the model that what we have developed for this product, for these readings, the model is not a significant model. Why? Because here you have to go with the fit statistics. We have to check it out. Okay. So the R square is really good for engineering problems. So this is also good, but we are going to do the experiment with the 95% confidence interval. That is, only 5% reduction is accepted. But in this case, 24% reduction is given. So actually, by statistics, it is not good. It is not good enough. And also you can see the predicted R square. You can see the predicted R square, which is minus. That is minus 433%. It is produced wrong. It will predict wrong. So that's why the model is not good. That's why the model is not good. Okay. So coded equations and all we can have here. Okay. So this is the coded equations. Now I am going with the diagnostic. So what is the problem in this? Why a significant model is not developed? That we are going to see. In the diagnostic plot, you can see. You can see this straight line fit is not possible with the residuals. So that's the important thing. Now you can see a straight line fit is not possible. So that's why the model is not significant. So then residual versus run, we can see, you can see the residuals are very, very less and it is going to be nearer to 0. Okay. Then predicted versus actual, you can see it is not at all good. The actual and the predictor is is being scattered and it is not lying on the 45-degree straight line. So this straight line is 45-degree straight line and the predicted points and the actual point, that is the experiment points, are not with each other. Okay. Then I am going to the report. Here you can see the actual value is this, the predictor value is this. You can see the maximum of 14.76 is the residuals. Okay, so the residuals has to be very, very less enough. Then only it will be a good one. Okay, then going with the model graphs. So this is the graph that shows what happens to the separation factor when there is a change in temperature. When there is a change in temperature. So when the temperature is being changed from 45 to 55, you can see the separation factor gets reduced. When it is further increased from 55 to 65, a further decrease in separation factor can be seen. Okay, so this is one. Then I am going with this vacuum. So it is almost the same. It is almost the same. So, but there is a decreasing trend. Then feed concentration. So initially with the concentration of feed from 20 to 510, there is a drastic increase in separation factor. After which it remains the same or a small change is taking place. So put together we can see it in all factors. Then the interaction plot can also be seen. So what it implies it? Both the lines are parallel to each other. So no interaction is seen. So I'm going to change it like this. 2. So on the right side I'm going to change. You can see this. The right side we have feed factor x1, then percentage. So this is for 30, this is for 60, and this is for 90. You can change this and you can have different graphs that you can include in your research articles also. So this I am going to take it as x2. Now for 510, what is the result? For feed concentration of 1000, what is the result? So that and all we can identify. So no interaction effect is seen between the selected input parameters. So that's what we are going to obtain here. So no counter plot will be developed. So this is the 3D surface. So previously it was a surface. Yesterday we have seen. In Taguchi we cannot have these things because we have selected only the main effects. If I am going with the 2F1 or 2F2, that is second order and higher orders, then only a response surface will be produced. Until then, these boxes will also be produced. So you can see the difference. So for 45, the separation factor is higher. When it is being increased, the suppression factor is to reduce. So that is what we are going to have. So for 20, what is the change? For 510, what is the change? If I am going to consider these as x2, what is the change? So for 90, for 30, for 60. So this is a visualization. This is visualization. So how perfectly we can determine, or what interpretation that what we are going to obtain by this. So scientific reasoning is very, very important. So these are all statistical tools we can analyze, but why this is taking place, that is very, very important. So that scientific reason is very, very important when we are writing the research articles. Then only it will be accepted. Simply I have obtained this because of this. If I go to write that, then the research articles will not be accepted. So this is going to decrease because of this. Okay, that statement should be provided in research articles. So this now I have analyzed. This I have analyzed now. Now after analysis, I have to go with optimization. So numerical optimization I have to go. Okay, so the inputs and all, it should be in range. And the output suppression factor, whether it should be maximum or minimum. So for I am going to consider this as maximum. The suppression factor has to be maximum. So you can see here bottom. The lowest value is 2.42 and the highest value is 59. So in the steepest ascent, I'm going to search in the domain, that is the problem domain or problem space, to identify the optimum conditions which fetches the highest separate factor. So in the steepest ascent, I'm going to select. Then I am going with the solution. You can see this. The solution and all, we can see. Okay, so what is the optimum condition? In the RAM plot, it can be determined. So the feed temperature is 5, that is 45, I hope so. Then vacuum pressure is second. And the feed concentration, it will be 2. Okay, criteria. Okay, the solutions and graphs we can determine. So this is how we are going to do it in the Design Expert software. Right? There is one more software that is called as Minitab. That also we will see now how to solve this. For Taguchi, this Minitab is really good. Than the Design Expert software. But for RSM, kindly go with the Design Expert software. So this is the Minitab software, the front end. Okay, now I'm going to do the same procedure in Minitab. So you can feel the difference between that. So in the first thing, I'm going with the stat. Stat is statistics, in which I'm going with the DOE. Then in that I'm going with the Taguchi. Then create Taguchi design. So stat, DOE, design of experiments. We have the factorial response surface methodology, everything in the software. And in Taguchi, I'm going with the create Taguchi. So it will be asking. So in the previously, it is from the drop-down menu in the Design Expert 12 that we have selected the orthogonal array. But here we have to select which is acquired. So 3-level design. Or in other words, you can just click the display available designs. You can see here. So single level, mixed level and all. Okay. So we can go with this. So for L9, you can see 3-level, 2 to 4 parameters. Okay. So 3-level, 2 to 13 parameters I am going to. So in which, how many factors we are going to have? I'm going to have 3 factors. So design, it will provide 2 designs, L9 and L27 I can take. But if I'm going to have limited resources, I'm going to choose L9. If I'm going to have better resources, I can choose L27. The purpose of choosing higher number of experiments is reducing the experimental error. The first thing is reducing the experimental error. In second case, the interaction cannot be studied in L9. Even though we are putting some graphs, interaction effect graph and all, the exact interaction can be obtained or determined only with the higher number of experiments. Okay, I will tell why or how after analyzing this output. So I am going with this L9 only. Okay. Now you can see these 2 tabs are getting highlighted, the factors and options. It is getting highlighted. Now I am going to click the factors. So here you can see the name and the level values. So the name and level values that what I am going to obtain is, so this is feed temperature. So previously in Design Expert there are 3 tabs. So I entered the value. So how to enter the value here? 45, then I have to leave a space 55, a space 65. If you are going to provide it as continuous, then it will take it as a single level value. It will take it as a single level value. Then feed temperature, then we have the vacuum pressure. Then it has the vacuum pressure. The vacuum pressure is 30, 60, 90, 30 space, 60 space, 90. Then I have the third parameter, that is feed concentration.
Feed concentration, sir.
Yes, ma'am. Feed concentration, that is 25,
25
10
mandals, sir.
and 1000. Okay. Just click OK. That's all. Now I'm going to click the options, store design in worksheet. Okay. Then OK. Now this we have designed. So no need to manually design the experiments. So the combination and all, the system itself will take care of. So that's the beauty of these softwares. Because Taguchi is a well-known experimental design that uses octagonal array. So these are being integrated in all the softwares. And now we are going with the output. The output I have to type individually. So separation factor that I have typed, then the values I am going to copy and paste. So now you can see the difference between the Design Expert and Minitab. In Design Expert, first column is STD, that is standard design, and second one is run order, that is after randomizing. But here it provides only the standard run. No run order, that is randomized order is not provided in Taguchi. But in RSM it is possible. But in Taguchi we have to do the experiments as per this design, and no randomization is done in this. Now how to analyze? The same procedure, stat, DOE, Taguchi, define. Now you can see these 2 tabs are getting highlighted. Previously only the create Taguchi design tab will be highlighted, and now these 2 tabs will be highlighted. Then define. What is the factor? The factors are nothing but the inputs. What are the inputs? The first 3 columns is my input. The feed temperature, vacuum pressure, and feed concentration. That is my input. So just select and click select. That's all. So that will come in this side. So I'm selected the input factor. Then stat, DOE, Taguchi. Now I am going to analyze. So what we are going to analyze? The response data are in. Only one is shown. Why? Because I assigned the inputs as factors in the previous condition. So only the output will be here select. Now we have different tabs here. So the first tab is graph. So generate plot of main effects and interaction in the model for signal to noise ratio and the means. Okay, mean is I'm not going to convert that into signal to noise ratio. So for this, what is the means? Okay, that I'm going to identify. So what is means in this? So this 45 is my level value. You can see here in the first one, feed temperature 45, 45, 45. So what I'm going to do is the separation factor 2.9677 plus 54.0590 plus 59.6777. That I have to add divided by 3 because 345 is there. So divided by 3. So that is one mean. Similarly for 55, similarly for 65. So that graph. So I don't need that. So I need only the signal to noise ratio. Then analysis. So analyze Taguchi's design. Display response table for Western ratio. So the main effects plot will be drawn only based on the signal, the response table. So this response table I am going to determine. Then fit linear model. So what is this actually means? So that is determining the ANOVA table for SN ratio. For SN ratio. If I don't want the ANOVA table, just uncheck it. If I want the ANOVA table, we have to check it out. So initially I am not going with this. I will tell later on. Okay. Then okay. Then terms. Whether I am going to consider only the main effects or interaction effects. So the selected items you can see on the highlighted side. A, B and C. That is the selected parameters without interaction. So on the other side, left side, you can see AB, AC, BC. These are all interaction effects. So I am not going to select this. So I am going to select only the available factors alone. Okay. Then options. This is very, very important in this. So what is our goal? That is my objective, whether to maximize the separation factor or to minimize the separation factor. So in this case, for example, I don't know exactly what is the separation factor, whether we have to maximize or minimize. I'm considering that it is to maximize. So here you can see the formulas that what I have told, shown in the slides. So larger is better, the nominal is better, then smaller is better. So now this is minus 10 log. I am not going to use natural logarithms. So larger is better. So that my objective is to maximize the separation factor. So okay, then click OK. You can see this. Okay, so the design summary, Taguchi's design, L9, number of factors 3, runs 9. So this is the response table for the signal to noise ratio. So based on this only, this graph is drawn. Okay, what is this? Larger is better. You can see this. What's my objective? Larger is better. Okay, that's my objective. Then main effects plot. Then main effects plot. So from this, I'm going to identify the optimum condition. That is, the maximum SN ratio is my optimum condition. Why we are going to choose it as maximum? Whether it is larger the better, smaller the better, I'm least worried. Okay, only the conditions that have highest S by N ratio, because S stands for signal, N stands for noise. When the noise levels are lower, the signal strength will be good. So the optimum condition is where the S by N ratio is higher. So in this case, the here it is higher. So the feed temperature is 45. In the vacuum pressure, it is 60. And in the feed concentration, it is 1000 grams per liter. So this is my optimum condition. So this is good. So I obtained the optimum condition. Now, each and every, the feed rate, how much it is going to contribute, that quantification towards this, what to say, separation factor, how much it is going to provide. That I am going to determine only from the ANOVA. Now I am going with the same procedure now. Stat, DOE, Taguchi, So here you can see the predict now. Okay, that I will see it later on. Then analyze. In the analysis, now I am going to click this fit linear model so that the ANOVA table will also be. Now you can see it here. The ANOVA table, the ANOVA analysis for SN ratio. So the degrees of freedom. What is this degrees of freedom? Feed temperature, I am going to 3 levels. So total degrees of freedom for feed temperature is 3 minus 1 level. So that is 2. So total it is going to be 8. Okay. So total 8 means total number of experiments is 9. So total degrees of freedom is 9 minus 1, which is equal to 8. Right? So this input parameter for feed temperature, it is degrees of 2, vacuum pressure 2, feed concentration 2. So total is 8. So 8 minus 6, the error is 2. So as told previously, the interaction effect cannot be studied with this L9. That's why we have to go with L27. Why? If I'm going to consider the interaction effect, that is AB, AC or BC, what happens? See, for example, if I'm going to consider the interaction between feed rate and vacuum pressure, then the degrees of freedom will be 2 into 2, totally 4. Totally it will be 4. But the residual error is already 2. So the residual error becomes 0 or it becomes minus. That also we will see. So that this ANOVA table will not be formulated. DOE, Taguchi, analyze. In these terms, I am going to choose all these 3. Okay, all these 3, these interaction effects I have selected. Now click OK, then OK. Here you can see. Right. The following terms cannot be estimated and were removed because you can see the number of residual error is, it will become 0. That's why in this case, the interaction terms cannot be considered. If I'm going to choose it as L27, it may be taken into effect. Okay. So one more thing is how to determine whether the model is good or not. You can see the R square value is 85.98% and the R square adjusted is 43.92. So 85 is really good for an engineering problem. So even though we are going to do this analysis with 95% confidence interval, what we have obtained is 86% confidence interval. That is really good with the experimental conditions and that too in laboratory cases. Okay. So which influence is more? That how to determine? We call it as, so I am going to copy this, copy, and then I am going to put it in a Excel sheet. Okay. Or okay, I'll tell. No need to Excel sheet. So what is the contribution of this? How to determine? So in research articles and all, you can see that last column they will be adding as percentage contribution. That is nothing but the individual sequential sum of squares divided by total sequential sum of squares. That I will tell. Okay, the first for the feed temperature, the sequential sum of squares is 53.03. The total is 950.74. So the percentage contribution is 5.58% only. So the feed temperature has contributed only with a meager 5.58%. For vacuum pressure, 21.88 divided by the total sequential sum of squares, 950.74 into 100, which is equal to 2.3%. So the 2.3% is influenced by this vacuum pressure. But for feed concentration, it is 742.54 divided by 950.74 into 100. So 78.1%. So the separation factor is influenced by 78% by the feed concentration alone. Feed concentration alone. So the residual error 133.3 divided by 950.74, and that will be around 14%. Okay, so like this we are going to determine the percentage contribution, that is individual sequential sum of square divided by total sequential sum of squares. So that is the formula that we will be using. Now here we can see there is no SN ratio, the value. So that how to obtain. So analyze options. Okay, storage. There is one more tab that is called storage, in which store the following items means. Okay. So here you can see the SN ratio, what we have determined will be displayed here. But the SN ratio for values cannot be displayed in Design Expert 12. In Design Expert, the SN ratio values that is determined by using the formula will not be displayed. So this is what we have obtained in the RAM plot in Design Expert. So these two graphs will be the same. It provides the same outcomes. Okay, so this is how we are going to work this Taguchi's DOE in both the Design Expert software and also in Minitab software. So 30 days trial version is possible with this Minitab, and that you can download, and also you can have individual licenses or for institutional prices, so it's also available for that. Okay, if you have any doubts in this, you can ask now for Taguchi. If you don't have any doubts, we will move on to the response surface pathology.
So what we measured is earlier design experts, we got the separation factor S by N ratio, no?
Yes, ma'am.
How much variation we are seeing here, sir?
So the variation will be the same. Both the software works in the same manner.
Okay.
The statistical way of doing things will be the same, but the results that what it will be providing will be different. So in Design Expert, we will be having the RAM plot. So first look at this main effects plot. Okay, this is the main effects plot you are seeing in Minitab, no?
Yeah. Okay.
That we will have now in Design Expert.
Okay. RAM plot.
So this is the how this will interpret. So the feed concentration, it will be different. It may be because of some values that I have changed. Some values changes that has taken place, that we can see. But mostly the two results will be the same. So some values I might have changed. That's the reason for this changes. So some colorful graphs we can develop and we have to interpret. That's the main thing. So this graph, what you are seeing is just the mean. We can draw it as we are seeing in a Minitab, but in a colorful manner, we are going to show it as a bar graph. That's all. Three-dimensional bar graph.
Okay, sir.
So both the software will produce us the same result, identical results. Only the way of a representation in graphs or something, it will be difficult. It will be different.
Okay.
In Minitab, we
The
can
presentation
store
of the result only different, but same
so
result.
value. The Minitab software will provide it as the worksheet itself, whereas the Design Expert software won't provide us the SN ratio. That we have to separately calculate.
Okay, sir.
Okay. Then we will move on to the response surface methodology. The response surface methodology, first I will start with a slide and then I will move on. So the response surface methodology, I hope this slide is visible now to everyone. So this response surface methodology, normally we call it as RSM, response surface methodology, is a specialized DOI technique because it combines both the statistical as well as optimization methods. So the statistical way of analyzing things and along with the multi-objective optimization. So this decision expert software is specifically useful in multi-objective optimization by using the disability approach. That what we have obtained the ramp plot and all. So in this RSM, we are going to have a group of statistical technique for empirical modeling. The empirical modeling is nothing but developing an equation for the output that what you have obtained. And then building and model exploitation. The building and model exploitation is nothing but the ANOVA and all, which is the statistical tools that we what will be using for interpretation of results. Right. So in RSM, what we are going to do is we are going to develop a response surface. The response surface. The response is nothing but the output. Okay. The response is nothing but the output, and it is being represented as a surface. And that's what it has got the name as response surface methodology. So the response surface is represented by this, the function of the inputs. The function of the inputs. Okay. So this is the surface that what we will be having. In the previous session itself, we have seen this three-dimensional response surfaces that is plotted between two inputs and an outputs. So it's a colorful graph. It's a three-dimensional representation between representation of relationship that exists between two inputs and one output. Okay. So in the first figure, we are going to have only the response surface. That is the three-dimensional plot. And in the second graph, we have both the contour as well as the response surface. In the contour plot, it is a two-dimensional plot drawn between three parameters, in which two are input and one is the output. So this is what we will be speaking about. Okay. So initially, we will be using only a lower order polynomial, that is y is equal to mx plus c. That is the equation of a straight line. Then later on, if the model is not good enough, that is, if the model is not well modeled by a linear function, then we are going to the first order equation. So here you can see y is equal to beta naught. So this is the input, and beta 1 is the coefficient for x1, then x2, then x4. That is the first order equation. If this is not going to be good, then I am going to the second order. The second order, what we are going to do is y is equal to beta naught plus beta 1 x1, beta 1 x1, then beta 2 x2, like this, beta 2 x2, similarly like that, plus beta 3 into the interaction effect between x1 and x2, x1, x2, what we will be considering, that is this. And also I will go with the beta 4 x1 square, and beta 5 x2 square. So this is a higher order polynomial. If the linear polynomial is not going to work, then I am going with the higher level polynomial. So this is how we are going to develop the response surface. The response is nothing but the output. One more important thing in RSM is we will have same number of experiments repeated to larger numbers. One particular experiment will be repeated many times. That what we call it as repetition or replication. Intendedly it is not made, by the design itself, the replications is being made. For what purpose? If I'm going to do the experiment, the same experiment again and again, and if I'm going to record that outputs, if I'm going to get the same or nearby values, then the experimental error will be less. So in order to avoid the experimental errors, some experiments will be repeated multiple times. If I'm going to get different values for the same set of inputs, then the experimental error will be higher. So there is some problem in the equipment or in the testing methods or like that. So we can avoid that, or we will go with the new setup. So that's the advantage of going with this RSM. So this is what we are speaking about. So yesterday itself we have seen steepest ascent, steepest descent and all. So here, this is my current operating condition. This is my current operating condition, and this is what we will call it as the design space or problem domain. Right? So from the initial conditions, I am going to move randomly. I am going to move randomly in search of the optimum condition. I am going to move randomly. And finally, I will be moving towards the optimum condition. Okay, so this is the path of improvement. This is the path of improvement. So once it is being moving in the right path, so that is called as the path of improvement. Then we have the steepest ascent. So for determining the maximum conditions, okay, I am going with the steepest ascent in this direction. You can see this. So y bar is equal to 10, the initial value. So initially I am going with this. Then I am going with the higher value because I want maximum output. So I am going to move in the ascending order. So steepest ascent. If it is the minimization problem, you can see this is the maximum one. My minimization is here 0. The minimum value that I can obtain is 0. So starting here, then I'm coming here, then coming here, and I'm going to move towards this. So this is called as steepest descent. This is called as the steepest descent. Right? Then we have a saddle point also. So what is meant by saddle point? The point that represents a maximum response and also a minimum response. So the same point will indicate a maximum and a minimum response, and that is called as saddle point. Right? So this is the surface with a maximum. Here you can see the maximum value is here. The surface you can see here. This is the surface with the maximum value. So this here we are going to have the minimum value. So this is surface with the minimum value. And this is the surface with the minimum value, and this is the surface with the maximum value, which is known as the saddle point. So in the same surface, I have a minimum value and I have the maximum value. So which is called as min-max condition. So that is called as min-max condition. So mini-max. Okay. So RSM experimental designs. There are two designs. Generally, we will be using these two designs also. The first one is the BBD design. We call it as BBD, box Benken design. So exactly it will choose. So in RSM and all, we will be providing only the lower value and higher value. So as provided in Taguchi, we don't have the level values. We have only the lower limit and the upper limit. The in-between level values, the system itself will decide depending on some criteria. That the criteria we'll see it later on. Okay. So the system itself will decide that. In box Benken design, the system we are going to provide the lower range and the upper range value. The system will exactly choose the middle value. The system will exactly choose the middle value, and it has lesser number of experiments than that of the central composite design. That is the another type of design. So one is box Benken design and the other one is the central composite design. When compared to the central composite design, this box Benken design will have reduced number of experiments. Okay, the system will exactly choose the middle level as one value. Okay, so how based on how the experiments are designed. So this is a cube. Okay, so this is one surface. In the surface, I'm going to have the middle of one edge, middle of another edge, middle of another edge, then middle of another edge. Likewise, 6 faces this cube is going to have, 4 sides, one top and one bottom, right? And also it has a one center point. So that center point will be for the total cube. But in contrary to the central composite doesn't have the edges. Instead of the center point of the edges, it has the corners. It has the corners, 4 corners, and for each surface it has the center point. So this is for the bottom surface. This is for this top surface. This is for left side. This is for right side. This is for front surface. And this is for back surface. And this is the overall point for the total cube. So because of which higher number of experiments is planned in central composite design. So the design space, okay, how many experiments that we are going to do will be decided based on the points, the axial points or the central points that we will be using. So this is what we will be having. So in RSM, we are going to follow the factorial design. That's all. So RSM follows the factorial designs. Okay, it comprises of center points. You can see the center points and then axial points. So which can be transformed into central composite design. So I am going to combine this. So the RSM comprises of factorial designs. Okay. Okay, this one all we'll see. So what are the different types of surfaces that we can obtain in RSM? The first one is the plane surface. You can see the linear relationship. Yesterday we have seen linearly it will be varying. There is no curvature. Then we have the quadratic surface. You can see quadratic surface, a curved one. Then this is a linear and this is a quadratic, and that is called as a ridge surface. Then we have the maximum condition and a minimum condition. This is minimum condition and this is a maximum condition. So min-max. So that is a saddle one. And the fourth one is the twisted surface. The fourth one is the twisted surface. It all depends upon the values, the outputs that what we are obtaining. So based on this only, we are going to write the explanations or interpretations from the graph. So what type of surface we have obtained, whether it is planar surface, quadratic surface, or a ridge surface, saddle or twisted surface and all, we are going to write. Okay. Now, the disability function. So yesterday itself we have seen that disability. So this is for maximization. So the maximization, we are going to move from the lower limit to the upper limit. You can see this. We are going to move from the lower limit to the upper limit. Okay. The ideal value for disability is 1. The disability varies between 0 to 1. Okay. 0 is undesirable and 1 is desirable. So it moves in this direction from 0 to 1. Okay. So for maximization, it moves from lower to upper control limit. Whereas in the lower the better, that is in the minimization problem, it will move from upper control limit or upper limit to the lower limit. You can see this. Then why this is going to move like this? Why can't it will move like this? Okay, why can't it move like this? Because I want the disability closer to 1. So initially it is 0 and it can move only towards 1. If it is going to move like this, then initially it will be 1 and it will be 0 at the final. So it is going to be the decreasing trend. It is not so. The disability should be moving always from 0 to 1. That's why we are going to use this lower the better concept like this. So this is nominal the better. In nominal the better, we are going to fix the target. Okay, and that's why we are going to have both the conditions of maximization as well as minimization. Okay, so this is the formula that is associated with this. This is the formula that is associated with this. So how many? So this is the disability value for maximum, the formula that is associated with this, the disability value for the minimum. For multi-objective, we will be using the overall disability, where R is the number of responses. So in this case, if I'm going to have one maximization and one minimization, then R is equal to 2. Then I will be using this value. Then as seen in the various plants that what we'll be using, this and all we have seen yesterday itself, right? So this is for biomass. So chemical oxygen demand you can see for pH value and for co-digestion factor. This is one of our research work. So we have done this. So the Q plants and all. So finally we are going with the multi-objective. So here you can see maximization. So from lower value to upper value. And this is also chemical oxygen demand maximization. Okay. So you can have this thing. One more advantage of going with a response surface methodology is I'm going to provide only the lower value and the higher value. But in Taguchi, I will be giving the range, the level values. 100, 200, 300 and 400. In Taguchi, the optimum conditions will be either 100 or 200 or 300 or 400. What happens if the optimum condition is 280? If the optimum condition is 280, it will provide us only 300 as the optimum. Why? So 300 is nearer to 280. So I can determine only that one. But the exact optimum condition can be determined by using this disability plot in R sum. You can see the pH value 7.02. The temperature is 48. So exact optimum conditions can be obtained by this R sum. But in the case of Taguchi, the optimum condition will be any one of the level values. No intermediate value will be provided. If it is 210, then obviously 200 will be the optimum condition. So that's the advantage of going for this disability plot. Okay. So with this simple introduction, I will move on to the hands-on training with the Decision Expert software. If you have any doubts in this simple presentation, you can ask me now. Okay, then I will be going on with this. Yes.
It's okay, sir. It's okay.
Okay, ma'am. Okay, ma'am. So the first one is new design. So this is the front end in which I will be going with factorial design and response surface, in which I am going with response surface, in which we have different one. So central composite, box Benham, optimal and all we can provide. So D optimal, this is so box Benham and central composite. So we'll be moving on with this central composite design because that has many to explain. Many things are to explain that. So first I will be going with an example. I will be going with 4 parameters. Okay. So if I add, you can see. So previously itself I have told the categorical is nothing but text. Catalyst 1, catalyst 2, catalyst 3. In numerical, we have to give numbers 100, 200, 300 like this. Okay, we have to provide it like this. So in this example, we have only 4 factors. The first factor is time. We have taken time in hour. Okay, the other things I will provide it later. Then second one is pH. Then third one is dosage. And the fourth one is concentration. There is no unit for pH. For dosage, they have given it as milligrams. And for concentration, milligram per liter. The ranges that they have taken for time is 6 to 10. I am not going to provide anything as we have presented in Taguchi. 3 levels or 4 levels I am not going to provide. Only the low and high values I am going to provide. For pH, they have considered only 1 and 3. 1 and 3 they have considered. And for dosage, 0.06, 0.1 they have considered. And concentration, 10 and 30 they have considered. Okay, here you can see 30 experiments. Okay, in the below you can see type full, block 1 points. Non-center points are 24, center points are 6. That is what we are speaking about, the cube. Okay, depending upon the number of factors, this cube will tend to change. Then alpha value 2, that I will tell, this is called as rotatability. In which direction we have to search towards the optimality. Right? If we are going to reduce, then we are narrowing down. Okay, that I will tell. Right. Now, in the first we can check the time. The unit is hour. Right. The low value is 6 and the high value is 10. But the system has taken it as 4 and 12. Why? Because the directionability, the rotatability, it is going to search in a vast area. Right? It is because of this alpha value. Then in the pH, you can see, I have given the low value is 1 and the high value is 3, but it is taken as 0. The pH is 0. Whether we can take it out, it is not possible. Right? So the dosage, we can have the concentration 0. Now, I am going to change the alpha value now. I will go with the options. Here you can see the rotatability. So the rotatability is nothing but in which direction we are going to move towards the optimal condition. Whether it is in a wide range or in a narrow range. Okay, it all depends upon our requirement. Now I am going towards phase center, which is equal to 1. So that I will tell. Now you can see the time, it is 6, 10. The minus alpha value is 6 and plus alpha value is 10. So whatever I have entered, if I am going to select the alpha value is 1, that is phase center, it will take as it is. It will take as it is. Okay.
So, sir, what is this alpha, plus alpha and minus alpha, sir?
This is called as rotatability, madam.
Rotatability.
In which we are going to focus. That I will explain in the later slide. Later thing. Now, then you can understand it easily.
Okay, okay, sir. Thank you.
Here in the type you can see full. So in my setup, it is not possible to run 30 experiments. So what to do? I can just click the full, then I can take it as small. You can see now. Instead of 30 runs, now it has reduced to 21 runs. So the system itself has eliminated some experimental runs. Okay, so that 21 runs is possible with the setup. So 9 experiments are reduced. So that it becomes a partial factorial. So yesterday we are telling like that, no? So the full factorial. So depending upon the descent resolutions, 3, 4 or 5, we can reduce the experiments. So based on that, we can reduce. So here you can see now. So previously, okay, in full, you can see the number of non-center point is 26 and center point is 26. In small, it has changed to 16. So I have taken it as a partial factorial. Right? Now the central composite is based on partial factorial. Now I am going to change it to full. So as madam has asked, so initially I will be going with 2. Okay, now just to look at the values, I have entered the time as 6 and 10, but the system has taken it as 4 and 12. Okay, now I am going to click next. I have only one output in this case, and that output is percentage removal. Percentage removal, finish. Right. Okay, this is what the system has generated. Total is 30 experimental runs. So here also we can see the standard run and the randomized run. The standard is like this, sort ascendingly. So this is the actual design, but now it has been randomized. The first thing what we should do after designing this is we have to save this. Otherwise, each and every time when we are going to design, this experimental will get changed. The combination will get changed. Okay, so the first thing that what we have to do is we have to save this design. Now you can see now. Now I am going to just make this ascending for your purpose. I have entered 6 to 10. Madam, kindly listen. I have taken 6 to 10. Now you can see 4 is there, 6 is there, 8 is there, 10 is there, 12 is there. So totally 5 level values it has taken. So the range is going to be enormous. So accuracy will be higher. So if I'm going to change the rotatability, then the accuracy of your prediction or obtaining the optimal conditions will be really good. Okay, the same thing now I am going to use. File save as, file new. Would you like your new design to reuse the same factors? Yes. Now you can see the same thing. Now I am going to change the options to face center. Okay. Okay. Then next, the same removal finish. Now it has another 30 sets, but here kindly listen. Kindly see this. The least number is 6 and the highest number is 10, and in between we have only 8. So now it has been narrowed down based on the rotatability value, that is alpha. Previously it was between, I have selected 6 to 10, but the system has taken a extended value of 4 to 12, so that it is going to search the optimal condition in the design space. But now I have fixed 6 is my lowest and 10 is my highest. So within this design you have to search. Okay, now here also you can see some experiments are being repeated. You can see now here. So here you can see the time is 8, pH is 2, and dosage is 0.06, and the concentration is 20. You can see, 8.8. It has been repeated. How many times? For example, I will tell. 8, 2.8, 20. This is 1. 0.8. This is 1. This is 2. This is 3, 4, 5, 6. So 6 times it is being repeated. So 6 times the same experiment is being repeated. The purpose is to avoid experimental error. If I am getting nearby values, then my experimental error is least. If I am getting different values, then there is a problem in my experimental setup. So from the experimental outcomes itself, I can tell whether my readings are good or not. So that is one more advantage of going for this RSM. Okay, now I am going to use this value now. At the experimental runs, I am going to just enter. Right. Now I entered my output. So analysis on the left side, percentage removal. So initially no transformation, then fit summary. So now this will suggest, the system itself will suggest which model is better for you based on the R-square value obtained. If I'm going to choose linear, here you can see the adjusted R-square value is 0.52 and the predicted is 0.3. In 2F1 the predicted is 0.59 and in quadratic the predicted is 80 and the adjusted R-square is 93. So you can see this. and based on this, the system itself has suggested go for the quadratic model. Go for the quadratic model and don't go with the cubic model, because some factors are influencing in the negative manner. So don't go with the cubic model, go with the quadratic model. So you can see this also on the right side. The sequential model, then model summary, you can see for linear model what is the R square value, what is the adjusted R square, what is the predicted R square and all. Okay. So similarly for each and everything, we can tell what is this, what is that and all. Okay. So predicted sum of residuals. So press SS is predicted sum of residuals. So that is also we can see. So in this you can see, so 93, the R square value is 96, adjusted is 93. But coming on to cubic, you can see when comparing with the quadratic, the R square value is 99. That is the ideal value of 1. The ideal R square value is 1, that is 100%, but it's 99. But here you can see the predicted R square, it is very, very low. It is very, very low. Right? So the system itself has suggested that quadratic model will be good for your output. Okay, then moving on to model. So here you can see the system itself has selected which is the model and all. Right? So here you can see, if I'm going to choose this AC square, A factor and the square of the C factor, then it has negative influence with another factor. You can see that aliased, that is producing negative effect or in the wrong way. So quadratic itself, or if I want, I can change this also. So linear, it will take only the inputs. Then 2F1, it will take the interaction effects. Then quadratic, it will take the square one. So that is what we will be speaking about in the introduction part. Then ANOVA, you can see the model is significant. But one more thing that we have to look into is the lack of fit. The fit has to be good. The fit has to be good. That's why lack of fit should be non-significant. If the lack of fit is significant, a perfect fit will not be possible. Even though the model is significant, the lack of fit is also significant. Actually, it should be non-significant. Then only a perfect fit is possible. So in this case, it is significant. Okay, just leave this. Then look at the R square value on the right. Look at the R square value on the right. Okay. Now below the right, you have the beta coefficients. You can see the beta coefficients, which is used for developing the empirical equations. This is the coded equations and this is the actual equation. So this equation alone is necessary for prediction purposes. So once this equation is developed, no need to run a vast or higher number of experiments. You can provide inputs to this equation and we can predict. So that's why we are going to develop this empirical models. So that's where the fuzzy logic, the artificial neural network or artificial neurofuzzy inference system comes into way of predicting the outputs without going for any extensive experimental setup. Once we have larger number of data, we can feed it into the system so that I can develop a model and that can be used for prediction purposes. Okay. Then I'm going with the diagnostics. Right. First, I'll go with the normal probability plot. So mostly a straight line fit is possible, but here you can see 2 points. The red point, standard order 29 and run order 17, and then this run order 25, standard order 7. That is getting deviated on. So that 2 experiments we have to rerun. So there is a problem in that, or there may be any measurement error in that experiment. So kindly rerun that experiment and then fit it perfectly in the normal plot. Okay. So 2 things. One is standard order 7 and 29. So check it with the report. 7 and 29 standard order or run order. Kindly take the run order. Okay. 17 and 25. So 17 you can see minus 12. You can see the residual minus 12, then 27, 25, 25, it is 16. You can see a larger deviation only for these two things. If I am able to reduce this, then a perfect fit is possible. So that's where we are going to identify where our data is wrong, where our data is right. So which experiment has gone over our control. That and all we can directly identify from the normal probability plot of residuals. Okay, then residual versus predicted, then residual versus run. You can see now, right? So this is what we will be speaking about. 25, run order 25. You can see. So that is out of control. Okay, but all the other things are within the control. Only this is the extreme condition. So kindly rerun this experiment number 25 so that a perfect fit is possible with the equation. So this is our point of interest. So this is our point of interest. Then predicted versus actual, you can see that point alone is getting separated out. So there is a problem in that experiment. So apart from this, all the points are fitted along the 45. This straight line is 45-degree straight line. So all these points are scattered along the 45-degree straight line. Okay. So then I will be going for the model graphs. So the perturbations and all we can see. So this is not linear because we are going with the quadratic model. So previously, yesterday, we have seen linear graphs in response surfaces. But now you can see quadratic curves. Okay. Then contours. Then 3D surface. This is what we are speaking about. So this is linear. That is, when the time increases, the percentage removal also gets increased in a linear manner. But here you can see, this is a quadratic form. This is in a quadratic form. That is, when the pH tends to increase from 1 to 3, the percentage removal is getting increased in a non-linear way. In a quadratic form. On the right side, we can see the dosage. Just right click that, change it to X2 axis. You can see now. Mostly these are linear type. Then concentration. This is flat. So no change when I change the concentration. So that's our thing. So now I'm going to change the pH to X1. You can see. So the relationship between pH and concentration that we are going to study. Now if I'm going to change this is what. Okay. So from this response plot, we are going to identify which is going to influence the more. And finally, I will be going to the numerical optimization. The percentage removal is my output. So the goal is going to be maximize. The goal is to maximize. Then the solution I will be going with. So here you can see, in between these values, it is going to give 8.49, not exactly 8, as I have taken in my case. So you can see the design. There is no 8.45. There is no 8.45. So here also you can see 6, 8 and 10. There is no 8.45. But in this case, we are going to get 8.45. pH also 1, 2 and 3 has been taken, but it is 2.62. So exact optimal conditions can be obtained by this RSM, by using the disability approach. Okay, so this is how we are going to work on this. So this is the report. So what higher 102? So here also you can take 103 is there, 106 is there, 107 is there, 14, 105, 16, 107, 31. You can see that 107.437. So 35th solution. So I can change this. RAM plot, 36th solution I am going to change. So the percentage improvement efficiency will be higher, that is beyond the limit when we are going with the time. So time should be 6.5, the pH value is also reduced, and the dosage should be higher and the concentration should be lower. So by doing this, okay, the percentage removal will be really good. Percentage removal will be really good. Yes, 37, 35, 107. You can see this difference. So according to our requirement, we can see this. Similarly, we have different outputs, then the multi-objective optimization is also possible with this. So if you have any doubts in this response surface methodology, now you can ask me.
So it is above the limit, no, 99.32. It's acceptable?
Yes, ma'am. Yes, it is also possible. With this dosage,
So
it is
max.
possible.
So, okay. So
If
efficiency graph we can come
have
like
to do
this.
the confirmation experiment, and we have to identify whether this is good or not. Whatever the optimal condition, it is good or not.
Oh, okay.
We have seen
So
that
with all these conditions.
Yes, ma'am. We have seen an equation in Taguchi, no, madam. Mu predicted and all. By using
So,
the equation, we can predict. Or in this graphically also, we can do. This is the prediction, ma'am. The percentage removal is the predicted one by the system.
okay.
So with these optimal conditions in the red, we have to carry out another confirmation experiment, and we have to see whether 107 is possible with that optimal condition. Certainly, it will be nearer to that. I can assure that.
Even if it is not possible, what we can do then? The
No,
model is predicted
no,
is
it will
wrong.
come,
No?
it will come. Because based on our data only, the system is providing us the results. If our experimental setup is good, definitely we will get it. So it is also
Hopefully
telling
it will
that
come like that.
experimental number 25. The run order 25 is out of control. So we have to reduce that error also. So then only our model will be perfect enough. So we finally
So that also we have to do. That order number 29 also we have to run again, and we have to find the new value. Then we have to substitute.
Yes, ma'am. Because you are seeing that it is totally out of control. Here you can see. This is totally out of control. This 25. It is out of the control limit. So
Then this graph will modify. It will also come closer to that straight line.
Yes, ma'am. In the normal probability plot, we can see the straight line will be, this point will also be fitted into the straight line.
Okay.
Then obviously the R square values and all will be good. It also be increased.
Okay. Then the ANOVA table, it will come as if we are making this closer to the straight line, then the ANOVA table, this lack of fit will become not fit.
Yes, ma'am. The R square will be, now it is 0.96, then it will be nearer to 0.99, and the predictor will also get improved. And also there is a chance that the lack of fit is non-significant. So with this technique, you can produce n number of research articles, madam. With this Taguchi, RSM and all, we can produce n number of research articles. Because chemical, it is very less, this optimization techniques. Only few persons are using, and they are producing excellent papers.
I did something, but I was not knowing that time also the result analysis and all.
Okay, madam. Okay, madam. If you have any doubts, you can contact me later also, no problem.
Yes, sir, definitely.
They can contact me.
Yeah, this RSM only I did. That's the thing. Now I am seeing that one. So, okay.
Now hope it is good, madam.
Yeah. I can do some more thing.
Yes, ma'am. Okay, ma'am. Any other doubts from student side?
They are going to apply only. Their PhD, their research, their project work is starting now only, sir. That's why. So they want to do that one. That's why we are conducting this course. Generally, they are going to apply that one, that results.
So if you have any doubts, they can ask me, madam. No issues.
Right.
Okay, madam.
So while adjusting the optimal condition, it will automatically change, no, sir, not significant like that.
Yes, ma'am. Yes, ma'am. You have to change that input output response for the particular input, which is getting
Yeah.
deviated from the state line.
Uh-huh. Okay, let me see, sir, and with my readings and all, I will come back to you.
Definitely, madam. Definitely, madam. Madam, I will be providing you some videos
Okay, sir.
from the channel website, so you can see all these things. How to solve this? This is one of the journals YouTube link.
Okay.
I have taken all these techniques and it has been recorded, and you can download it and you can use it. That I have provided you now. The students can also watch. But there are many techniques. AN and also fuzzy also is there. Regression analysis. They can watch and they can have the hands-on training also that is being given. So it will be very, very easy and useful for them.
Yeah. This is the main thing we record now. Everywhere we are doing many experiments, and we have to see which one is the optimum conditions and all. It's very difficult for us to say that one without this kind of softwares.
Yes, ma'am. Yes, ma'am.
So, okay. So it's very useful thing only. There are different methods also. We can use.
Yes, ma'am. Yes, ma'am. In that it will be having a finite element that is not good for relevant to you. So artificial neural network is there.
Yeah.
In math, how to do the artificial neural network. Then fuzzy logic is there.
Yeah. That's also coming in this one, sir. Artificial neural network.
That is for prediction.
That's a prediction method. Prediction.
Yes, prediction, madam. That the fuzzy logic and the artificial neural networks are prediction models. Like the empirical equation that we are developing now, madam, that is also like that.
Oh, yeah. Okay.
So gray relation analysis is another multi-objective optimization. The principal component analysis providing weightages. If I have 2 to 3 outputs, then I can give equal weightage, or I have to change the weightage according to the outputs. So for this, the principal component analysis can be used. So the basics of analysis of variance. Yesterday, students are asking how we are getting on. This will be elaborated in the presentation.
Okay, sir. Anybody have any doubts? Can ask.
No, sir. No, ma'am. It's clear.
Ma'am, I think we have to proceed with the one examples in our own level and based on this discussions, I think. So
Yeah.
further we will discuss with the sir also for any step-by-step procedure, anything if it is tracking.
So I will be uploading some papers to Arun sir.
Yes, sir.
What I will be uploading some papers to Anu sir, that what I have downloaded for my for doing this analysis. So the students can go through that. So the students can go through that so that it will be easy for them.
Okay.
Okay, sir. I will share to them then. Okay, sir.
Definitely, sir.
So, okay, here this link in chat box, sir shared one link of YouTube video, I think, so that we can use. So, ma'am, then anything we want to clarify? Shall we?
No doubts later, and then we can.
So, Senthil sir, anything?
No, sir. I have finished my part.
Okay, sir. Okay. So, ma'am, shall we wind up then?
Yeah, yeah. That's okay. We can see all these things and we can come back to sir if we have some doubts. I think so. That's,
Definitely, madam.
yeah. Anyway, it's a fantastic presentation, sir. Learned a lot. Learned a lot. We can use so many things also for the help of this design expert. Anyway, it's
Okay, madam.
a
Okay,
very
madam.
nice presentation, sir. From which
Thank you,
you
madam. Thank you.
started also. I think students also followed everything, understood the basics. Let us
Thank
see,
you,
sir.
madam. Thank you.
With our experiments and our projects, we will include all these things in our projects, and let us see that one how can we. Anyway, we will contact you again, sir. Some doubts and all, we
Definitely,
will
madam.
definitely. Yeah.
Okay, madam. Okay, madam.
So,
We'll help in the right way, madam, to the students.
yeah, sir. Yeah, Anu,
Yeah,
then we can.
ma'am.
Yeah.
Ma'am, if there is no other further questions or queries from student side or anybody, we can wind up the session.
Yeah, that's okay. 2 hours.
Amal sir is there in our list. Whether sir is any something want to
Amal,
share
you
or
can. Amal is there means you can say something.
No, no, sir,
Amal?
fine. I was also listening. I understood whatever sir told. We have to practice, I think.
Yeah.
Thank you.
thank you, sir. Okay.
അന്ന്
So,
ആരെങ്കിലും ഓട്ടോ ട്രാൻസ്ഫർ എന്തെങ്കിലും പ്രൊസീജ് എന്തെങ്കിലും പറയാൻ ഇത് ചെയ്തിട്ടുണ്ടോ?
ma'am.
ആ എങ്ങനെ ഷെഡ്യൂൾ ചെയ്തേക്കുന്ന സാറിന് താങ്ക്സ് പറയാനാണോ അതോ?
I will express my sincere thanks, ma'am.
Yeah.
Very good evening to all. So today's workshop on design expert software was worthful. On basic level, we could get some idea about the development of optimization studies and all through design expert software. So, on behalf of the Department of Chemical Engineering, TKM College of Engineering, and TechUp 2, uh, we are expressing our sincere thanks and gratitude to Dr. Senthilkumar sir. Thank you, sir. Thank you for your sharing your knowledge and valuable uh, suggestions and doubt clearance were very helpful to us. Thank you, sir. Thank you very much, sir.
So I have to thank Dr. Mubarak Ali for this
Yes, sir.
opportunity. Also for
Yes, sir.
today, Madam Femina Madam and Dr. Anu sir for this opportunity to share our knowledge to the student community. Thank
The
you, sir, and
last
thank you.
2-3 months we are searching for people because all were in home now.
Yes,
This
sir.
day before last week only Mubarak sir was telling you can explain everything because the last time you presented now you came for FDP. That time I was not
Okay,
able to
okay.
attend that one. I thought of attending that one, but I went to Trichy. So that's why I was
Okay,
not
madam.
able to attend that one. I was totally disappointed because of that one. Then sir told I can again ask Senthil sir to give you a presentation like that. He was telling.
Okay,
That's why we contacted you.
I also have the
Sorry,
procedure in
sir.
a word file. That
Sorry,
also
sir.
I will. I have a word file.
Okay.
What to do, what procedure to be done.
Yeah,
That
sir.
also I will send it to Anu sir, so the students can also have that.
Okay, sir. Okay.
So,
Okay. Anyway, it was a very good experience. Anyway, thanks a lot, sir. Anyway.
Thank you, madam. Thank
so
you. Thank
we
you,
will.
sir.
I will mail you, sir, regarding further details. Further details, I will mail you, sir, regarding that, and we will.
Sir, are you? Can you take ANN and all, sir? ANN and
Yes,
artificial.
ma'am.
Sorry, sir.
Definitely, madam. Definitely, we are working on that only. ANN, fuzzy, ANFIS, and all we are working.
Okay.
And you are generating papers.
Okay. Let me see, sir. Then how we are getting time and all, I will contact you. Okay.
Definitely, madam. Definitely.
Let me see this one first. How students are making efficient. How it is efficiently they are processing this software. Then I will see that.
Okay, madam. Definitely, madam.
Okay. Okay. Thank you, sir.
Okay,
Thank
madam.
you very much.
Thank you, madam. Thank you. Thank you. Thank you, Dr. Anu, sir.
Thank
Shall I
you, sir. Thank
officially
you.
leave?
I will communicate with you, sir, through mail and WhatsApp.
Okay,
So
sir. Okay. Thank you. Thank you. Thank you.
we
Thank you.
can further. Anything? Have you asked anything, sir? Because here
Ma'am, shall I
rain is.
officially leave?
Okay, sir. Okay.
Thank you. Thank you.
So,
Thank you.
okay, we will contact. Thank you, sir. Because of rains, heavy rain is coming here, sir.
Oh, okay. Okay. No
Wind
issue.
is also there, I think so. Yeah.
So thank you, sir. Thank you. We will communicate.
Okay, Anu, I am
I'm cutting.
leaving.
Cut ചെയ്യാലോ അല്ലേ? Okay.
ഭയങ്കര കാറ്റ് കിടക്കും. ഞാനൊരു ജനലൊക്കെ അടച്ചിട്ട് എ സി
ഭയങ്കര
ഇട്ടേക്ക് അതുകൊണ്ട്
സൗണ്ട്
അറിയാൻ
വോയിസ്
പറ്റുന്നില്ല. പക്ഷെ
ഭയങ്കര ക്ലിയർ. ഇപ്പം
ഭയങ്കര കാറ്റടിക്കുന്നെന്ന് തോന്നുന്നു. നോക്കട്ടെ. ശരി അപ്പൊ ഓക്കെ.
ശരി.
താങ്ക് യു.
സൽമാൻ ഓക്കെ ബൈ ബൈ.
Okay, sir.
Hello. Hello.